It's not the last day of school yet. We still have a party. Aren't you coming on Saturdays? You'll teach us.
Oh, that's true. Yeah, that's true. Okay, thank you for saving me. All right, so let's talk about physical optics, sometimes called wave optics. So there's this whole idea where light is both a particle and a wave. It exhibits behavior of both because it is both. And so we can think about it as a particle for some optics. And there are some optics that we can't think about it as a particle because a particle would never behave that way. That other branch we call physical optics or wave optics, and that's what we're going to talk about with the second half here. There's only a couple things y'all really need to understand there. One is just kind of general wave interactions. So interference is one of those things. Reflection is one of those things from a wave perspective. And then we also need to talk about the double slit experiments. You understand how that shows that light is a wave. I'm only covering that from a conceptual standpoint today, but you also need to be aware that there are mathematical equations you'll be expected to use in the AP test. But they're not that hard, so I'll just let you guys figure that out later. I'd rather make sure you understand like what's happening. And so that's my focus today. So let's get into it. On the agenda, we don't need to do all those things or those things. All right. So, wave physical optics, I just said all these things, right? How do we know light's a wave? I'm going to prove it to you later, or at least talk about how we know. So let's talk about wave interactions. The first thing you need to be familiar with is diffraction. That went the wrong way. So, refraction is when light bends. Diffraction is when light passes through an opening and spreads out. So if light were a particle and I shot it through an opening, I would expect that it would just like pass through and create, a beam that matched the opening size. Does that make sense? If you take water and you push it through an opening, like you make waves, you put a wave generator with an opening, what you'll see is that the water will go through the opening, right? And then the wave will spread out. It will continue around, right? In like a ripple direction. How much it spreads out depends on the opening of the size of the opening. So you can see in the kind of GIF here what this looks like. I've got wave fronts hitting here. Notice that there's a barrier there, but what I see on the other side is that the wave front starts here, but then it spreads out in an arc. That's called diffraction. It's something that you can visually see with water, but we also can observe it happening with light. In fact, the double slit experiment is a way to test to see if that happens. We'll get into that later. This name is pronounced Huygens. So Huygens' principle describes this phenomenon, and it's what tells us that the closer the wavelength is to the size of the opening, the more it will travel through. This is why like sound travels through your home really well, but light doesn't. Because sound diffracts really well through things like doorways, because the wavelength is really close. But with light, the wavelength is really small, and so it doesn't diffract well through things like doors, because the opening is not very close to the size of the wave, and so it does diffract a little bit, but not a lot. If you actually look at the shadow through a doorway and you zoom in on the edge, you will see it's not a clean line. It's not like, perfect light, dark, meeting at one point. Whoops. What actually happens is the light slowly dies off into the dark. The reason for that is diffraction. It's not something you can see with your naked eye, but if you're able to look at it up close, like under a microscope, then you would see it. You'd be able to see the gradual shift. That's because of diffraction. It's not something that humans were ever aware of until we had the technology to see it, but it is a thing. All right. So diffraction, important point is that as waves travel through an opening, they will spread out. And this is true of every wave, which means it's true of light, just not on the observable level with what we do. All right. Now, interference is when waves come together. So if you watch this GIF, you'll see the two waves are traveling towards each other, and they overlap for a moment. And when they overlap, they interfere with each other. This GIF is showing what we call constructive interference, where they come together and they build on top of each other. And so the wave amplitude increases for that moment because they're adding. You may not be able to see it from where you're sitting, but you can see the blue and the red are tracing the wave. And where they overlap, you can see where the waves would be. And you can see how they must be adding during that region. And so what we get here is that they add up together. You can also have the opposite, which we call destructive interference. So if I have a wave amplitude that's up and a wave amplitude that's down, and they hit each other at the right point, then they will destroy each other, hence the term destructive interference. If you have noise-canceling headphones, this is how they do that. There's a microphone on the outside that records the ambient noise, and it plays an inverted signal in the headphones, which destroys the outside signal, and so you don't hear it. Does that make any sense? So that's, it's fun stuff. People who don't know physics might think that it playing more noise will do damage to your ears, because it's going to be like more noise, but the whole point is that those waves literally destroy each other when it hits your ear, and so there's no increased energy going into your ear, so no damage to your hearing. All right, so reflection for waves. Important to understand that when a wave reflects, it doesn't always reflect the same way. Nope. There. Okay. So when a wave bounces back, so when we look at reflection off of like a mirror, all we care about is that it reflected. If I want to understand how that wave is going to behave as a wave, then I have to understand what's going to happen. So when it reflects, it's going to bounce back reversed. Because whatever bit hits first is going to come back first. And so if the wave is traveling, like this. So if I'm the wave, bloop, bloop, and I'm going to the interface like this, well, my tall edge is going to hit first. And so when I reflect back, I'm not going to reflect back like this, as if I bounced. I'm going to reflect back like this, because my big edge is going to continue to be moving first. Does that make any sense? Now, what we also see when we hit boundaries is that a wave could reflect. It also could reflect and invert. So there's another important term here. Reflection is like horizontal. Inversion is vertical, right? So depending on the boundary behavior, the wave may hit and reflect without inverting, or may hit and reflect with an inversion. And you can see here, if the boundary is fixed, it will invert. If it's free, it won't. Fixed is easier to see with mechanical stuff. So like, if I tied a knot onto this and I was making waves with a string, where the string is hitting this, it's not allowed to move. So that's a fixed boundary. Does that make sense? If instead I had like a loop over here where it was allowed to move up and down as I flick the wave, then this part would be allowed to move. That's a free boundary. Does that make any sense? And so that's where I would see no inversion. Here's a gift. What do you see here? So I have an incident wave, which is on the black string, and then a weird thing happens where I get a wave coming back and a wave going through. Why? Opposite. So it's not inverting because it's a free boundary. But here's the deal. What I want you to see here is when I change media, I get a wave that continues through, right? And I get a reflected wave. This is what we were talking about before, right? So I get some that goes through and some that's reflected. Just reminding you that that's still a thing when we look at the wave behavior. We might still see some energy be passed through the interface and some bounce back from it. All right. On to applications, like if we take all these principles and we start applying them to things, what do we get? So diffraction patterns are the first thing. So the double slit experiment is extremely important to physics because it's how we're able to actually prove that light is both a particle and a wave. So we talked about these diffraction patterns, right? So what what would I expect to happen? Let me actually draw a picture. That would be the best way to do this. What I would expect to happen if I shine light through a double slit experiment, which is like two slits like this that are close together, if light is not a wave, if it's just a particle, then if I had a screen over here and I shine the light through, I would see the light just pass straight through it, and I would get two bright spots where the light is hitting. That marker sucks. Right? That's what I would expect if light behaves as a particle. Does that make sense? If it only behaves as a particle. If instead light is a wave, then if I can make these slits close to the size of the wavelength of the light, then I should see that as the light passes through, they're not going to continue on. Instead, they're going to diffract, and I'm going to get curved wavefronts from both of these. Now, if that happens, then what I will see is that if these lines represent the high amplitudes, what I should see is that every time these two lines cross, I should see constructive interference. Whatever. I should see constructive interference, which means I should see bright spots, right? Now, there in the middle of the air, I won't see anything because light's not visible unless it's reflecting off of something or hitting your eye. So I won't see anything there. But then what I should see is on this screen, you may notice the pattern here that I'm going to get a lot of interference in the middle and then less as I go out, but there will be sweet spots. So what I would expect to see is a very bright center with bands moving away from it, where each of these locations where it's bright, I'm seeing constructive interference, and I'll also see the opposite in certain places where the light will be canceling out with the other wave, and I'll get no light. So I'll see very bright, and then I will get very dark, essentially no light at all, and then it will basically spread out between those in a gradient. This is why we call these diffraction gradients. Does that make sense? So there was an experiment done a long time ago where we shot a laser at these things and we tried to figure out, okay, if they pass through and I see two bright spots, then light is only a particle. If I shine them through and I see something like this, then it's a wave. And spoiler alert, it's a wave. And we end up seeing the diffraction gradients like this. So I used to do these for y'all. I don't have time. Classic. So it's really easy to do this at home, right? If you take a sheet of aluminum foil and an X-Acto knife, you can cut two little slits really close together and shine a laser on them. And if the room's really dark, you should see something like this. And notice you see very bright in the middle, slowly dying off to black, and then building back up, and then dying off, and building up, and dying off, just like the prediction there. Because these are the spots where I'm seeing lots of constructive interference, destructive interference, constructive interference, destructive interference, and so on and so forth. Does that make sense? It's very important that you understand why this pattern exists. Okay? So I'm going to pause for a minute. Are you okay with why this pattern exists? Okay. Here's a picture that's probably better than mine. Where you can see here that this orange line, it might be hard to see from where you are, but I'll post these slides, is actually tracking and tracing along with where all the constructive interference is happening. And this other orange line where it says min is tracking all of the destructive interference. And so you can see where we're getting those mins and maxes and how they line up with the pattern. Is that y'all? Holy crap. All right, really quick, you actually see a similar phenomenon with a single slit, not that important. If you do multi-slits with white light, you can actually make this work with white light as well. You just get rainbow patterns. Really quick, if you look at light, there are times when it's appropriate to think of it as a wave and times when it's appropriate to think of it as a particle. Here's a little table to help you think of what behavior will help you understand it. So when you look at all these, you can see what applies. Notice interference, diffraction, and polarization, those do not work with a particle view. The photoelectric effect also doesn't work with a wave view. So if you want to look and try to understand these things, there's something you can use for it. That's it. Sorry for going over a little bit. You'll have a good day. I'll see you tomorrow.